Right. Yeah, the little seminar that I'm going to do today is going to deal with steels, mechanical testing, phase diagrams, and heat treatments, and mention a little bit about the project that Mr. Goody is going to do this summer. Okay, and this past summer, as Dr. Rincon said, we did a project with Tyler Dalkey, and this is really a continuation on this. Okay, but in order to do this project, you have to have a little bit of a background on material science, and Mr. Goody will actually have to do some testing also on materials, and then we'll talk a little bit about his project also. Okay? So steels, mechanical testing, phase diagrams, and heat treatments, and it's almost like a little miniature material science class here. So yeah, there's many different types of steels. Okay. And these are some of the general groups of steels, but there's literally hundreds and hundreds, maybe thousands of different types of steels. Because do you know what steel is mainly made out of? Iron, right?
Yes,
Iron and some carbon, and then some other elements in there, you know, and depending on what type of alloying elements they put on there, you can get many different properties, right? And they make steel in the steel mills, right? Many different types of steels, and you see there, you know, the ferrous metals there, and here that we're breaking it down in cast irons. Okay, they have a lot of carbon in them, and then the cast irons. There's many different types of groups in there. Again, everybody's familiar with gray cast iron. You know, this has that smudgy feeling to it. But all these other irons, they actually have gone through a heat treatment, you know, a heating process in a furnace and a cooling furnace, and you can change properties. So that's how you get many of these other cast irons, or irons I should say. And then the steels, you see what they call the plain carbon steels. Okay, the plain carbon steels, they're steels that have mainly iron and carbon in there. Now there's still some alloying elements in there, but very small percentages. Okay, and then you have medium and low carbon and all that. And then alloying steels, well, they have a lot more carbon in it. A lot more alloying elements in there in different percentages that you can have. And that's how the steel mills, they make different properties by doing these alloying processes, and also some heat treatment processes. You can change properties considerably for materials. And you see here some familiar ones like stainless steels. We're all familiar with stainless steels. Even in the stainless steels, there's many different types in there again. So just like in any field, you know, it's very broad. Stainless steel has a lot of chromium in it, right? And the chromium reacts with the oxygen, you get the chromium oxide skin. That gives you the corrosion resistance, by the way. You know, but there's many different types of stainless steels, and then you see tool steels like they use in dyes and all that. And there's many types of that. So that this goes on and on. But that's a kind of an idea. And the project that we are going to do this year, but it's a little bit different type of project than last year. We're going to, if you have an unknown steel, which you see a lot of job shops, okay, that people, they buy some material, they know what it is, might even be labeled, okay, and they know, okay, that was a 1040 steel, okay, a plain carbon steel. That's what 1040 stands for. 10 is just plain carbon, 0.4, the 40 is really 0.4% carbon, okay? It's labeled. And then they use it, and then there's some scrap left material that they could still use, but they lost the label. And all this stuff is sitting around in the shop, and they don't know what it is, okay? And, you know, now they have to use some material, and again, they need to use it, and they don't know what they got. Okay, well, there's spectrometers that they can use, but they're very expensive, right? So last year's project is where Tyler Dalkey, he used a grinder, okay, and then you hold a piece of specimen of metal there at constant force against this grinding wheel and a specific size, and it creates sparks, okay? And it creates a spark pattern, and by looking at the spark pattern, you can distinguish between different types of steels. That's really what he discovered. He looked at about 10 different types of steels, okay? And now there's definitely improvements that, honestly speaking, can be made on this project that he did, this paper that he wrote, and the experiment that he developed. But what I'm going to show you pictures of what was done, but basically he looked at the spark pattern and used this as a way to create a little atlas, and by taking pictures of these spark patterns and then comparing different types of steels against each other. Okay, so but this time we're going to do it using a camera, so you can see that. Okay. Okay, here's some of the alloying elements and reasons why people add alloying elements to different types of steels. Okay, and you know, like you might see there, like lead, for example, improves the machinability. Okay, you see Ni used as a toughener and corrosion resistance. You know, copper, chromium, you know, you name it. And here are the different percentages. You don't have to exactly stick to it, but here they explain some of the major functions. Well, going back to that grinding test, if you have a grinding wheel that rotates, let's say at 2000 RPM, okay, and you hold a specimen against that grinding wheel, it creates a spark pattern, okay. Well, in the 60s, there were some people that actually did research on this and really created a huge atlas of different types of spark patterns, and they can tell by looking at that spark pattern. Oop, oh, there's some silicon in there. Oop, there's a little bit of this in there, which it's amazing. They must have had years of experience, and there were people that did that in the steel mills and could actually look at the spark pattern. Now you will see that Tyler took a different approach because he only had basically a month-long project, and to learn all that is amazing. Now we got that Spark Atlas book, we got it through Interlibrary loan. We have it actually now too. But, yeah. Now here, yeah, this is the American Iron and Steel Institute, the coding system that they use, or the Society of Automotive Engineers, and they use different types of steel codes to designate, you know, a steel type. Like for example, you see here the 1, right? That's a carbon steels, and then 1-0, that's a plain carbon steel, and then you see 2 dots there that are left open here. Well, like if it was a 1040 steel, I already mentioned that, and the 40, well, that's not 40%, it's 0.4% carbon, okay? If you see here like a 43, let's say you have 4340 steel, that will have molybdenum in it, chromium, and Ni nickel, right? And then these are approximate ranges of the alloying elements, but you know, it will matter how much is in there. But that's the steel codes that they use, and there's a whole bunch of those, right? And then you can change them again by giving them specific heat treatments. Like in the material science class, we have several heat treating furnaces, and we can do some heat treatments and change properties too. So when you get an unknown steel, you don't, if you don't know anything, you don't have a history on it, right? So because it got lost, you know, and then it's difficult to figure out what you got. Now, one thing is different between different materials and different steels is that the strength properties are going to be different. Okay. And we'll actually have Mr. Goody also do some tensile testing in the lab, and you know, of some of the steel samples that he learns how to do tensile testing. We're going to have him do some hardness testing. This is an example of a hardness tester here. This is a machine here, and you put a specimen in there, a tensile specimen, and you just pull on it. It's a pull test, okay? And the material starts to strain, and because the force get larger and larger, eventually the material will break, right? And we can create what they call stress-strain diagrams out of that, engineering stress-strain diagrams. And you know, we can look at the strength properties in a second. I'll have some graphs of that in a second. We actually just purchased a new tensile testing machine. We'll still have the old one, but we bought a brand new tensile testing machine. We just paid a lot of money for it, and it was unbelievable how they got that machine in the building there. I mean, it's like a huge machine, and well, none of us, I should say, including myself, had really thought about how to get that thing in the door. Well, they did get it in. They brought it in with a forklift. First of all, they had the forklift that we have for the maintenance department is not strong enough to get it to the door. So they had to actually borrow the forklift from the people that are doing the construction on our building. They have a bigger forklift. So they got it to the door. Well, then 4 huge maintenance guys were there. They were looking at it, this is not going to work. So then they called up and you should always do this if you have any trouble, call the football team. I got 10 guys, I'm not kidding you, 10 guys, plus the maintenance guys. And and Mr. Weller was there, and another student helper. And I understand they all had to lift it into the building, get it in there, and it's sitting in the corner now. So we got it in there. We're still getting it set up, and it needs to be calibrated and all that stuff. But it's amazing. So we hope maybe that you get a chance to use that machine also and do that. So here you can do tensile testing in here, but you can also do compression testing, okay, and different materials, different steels have different compression properties. You can do Burnell hardness testing in that, and we'll have you do that also. Burnell is just a hardness test where you make an indentation in there and you measure the size of the indentation. Again, you know, different materials have different strength properties. So these are all helpful tools that can kind of narrow things to get more information about this. So that's why I have that in there. And so yeah, that's the compression testing there. You can do even shear testing in it if you have like a what you call that, like a bolt, and you have 2 surfaces like this, and you have a bolt and you apply forces to it, and the bolt can shear. Okay, you can do shear testing on that machine too. And we have that capability too. This is an example of a tensile specimen here, and this was screwed in, and they can pull it, and you see this one hasn't broken yet, but it's starting to neck there in the region there. That's the weakest region there, and it starts to neck, and eventually it will break apart. And what you do to calculate the stress in the material, okay, which is called the tensile stress, sigma, that's the load P divided by the original area. Now, the original area is just the diameter here of the middle here, what you had in the middle, okay? And to calculate that stress, they just, you know, they do this, the rho divided by the original area is quarter pi d squared, which is the original diameter squared. They call that the engineering stress, which is really incorrect if you think about it, because that area is getting smaller and smaller, right? But to simplify things, we use that engineering stress. There's another thing that's called true stress, but in the true stress, you have to divide by the instantaneous area. You constantly have to keep track of what that diameter is, but that's a more time-consuming process. And so we don't use that. And also, that material is getting longer and longer, right? If you put a mark here originally here, and right there, and let's say between those marks it's 2 inches, well, that material will start to strain, it elongates, becomes longer, right? And you can show the engineering strain that's called epsilon, which is the delta L, the change in length, divided by the original length, okay? And that's the way we're going to plot the engineering stress versus the engineering strain. And materials will go through an elastic deformation process, and they will go through a plastic deformation process. Elastic deformation is just like a rubber band. If you have a rubber band and you pull on it, it goes back to its original dimensions, right? When you apply an initial force to a material, and if it's a small force, it goes right back to where it was. Let's say if you had the marker 2 inches, it goes right back to the 2 inches. Right? Plastic deformation, that's permanent deformation. If you take it beyond what they call the yield point, then the material starts to yield. It starts to permanently give. Okay, so permanent deformation takes place. This here is an example of the engineering stress versus the strain diagram. And then over here you see the stress, that's plot here. And then over here we'll see the strain here. Now, going back 1 second, what do you think the units of